You're ready.
Starting the stream, so Joshua, you're checking?
Sure.
And can you, Alex, also turn the camera so that it records Mike, because now it's recording everyone else, but
It's recording everyone else.
like it's Leslie and everyone.
Do you want me to sit over there or something? Is it
More,
better?
more?
Is it better over there or?
More, more? Okay.
Like this?
Yeah, yeah, this is pretty cool.
Harmless. Yeah.
It's pretty cool.
It's pretty cool.
Dishes are done.
Yes.
That doesn't
And
sound too
dishes are
bad.
done, so we're all set.
Yeah, alright.
So I think we're ready.
It looks
to go.
spectacular.
Want me to go? So,
Bless you.
I've got two pairs of glasses, and it's very confusing about which one to use. Which pair, rather.
I like it.
So this is talk about fractals, actually. I'm going to go through the maths of fractals, in specifically what they call escape time fractals, but we'll find out more about that in a bit. This was originally something I did ages ago because HTML5 had just come out. It's now rather old hat, but and I was quite excited about the canvas element that allowed us to draw directly in web browsers. But anyway, let's go through it. So why doing this talk? I like fractals. They're pretty good to look at, and it amazes me how such beauty can come from a simple little bit of maths. It's good. It's a good little maths meets programming meets pretty pictures meets art kind of a topic to cover. It means I keep my brain active by thinking about some hard sums and actually doing some coding. And I can grow them on the allotment too, like that Romanesco broccoli that is behind the screen there. Although mine, when I tried to grow them, they didn't look like that. They were small and covered in caterpillars. What's a fractal then? Let's have a look at it then. It's an object which has some of these properties, self-similar. So when it says some of these properties, they don't all have to have the same set of properties. So they're self-similar, so the same patterns repeat themselves at different magnifications. So you can kind of see on the right there, you've got the black bit of that is a close-up of the Mandelbrot set, and there's a sort of left branch of it. You can see a little black blob. The resolution's not very good, but that would be another copy of it, so it's got a similarity in there. It's got a very fine structure at all scales. It can be described. It can't be described by Euclidean geometry, so you can't use the kind of standard Euclidean way of describing things like waves, triangles, circles, and squares to describe them. It generally has a kind of simple and recursive definition, so they involve recursion, and they apparently has a Hausdorff dimension which is greater than its topological dimension, which I don't really understand. Anyone understand that?
What's a Hausdorff dimension?
Exactly. I think it means that its boundary is greater than the
Sounds
area
German.
it's bound. It's bound. So the interesting thing about things like the Mandelbrot set, which we'll see in a minute, is that the its boundary is almost infinite. It's got an infinite boundary to bound something that's finite in size, which is a kind of peculiar quality. There's various types of fractals. So there's random ones. There are things called strange attractors. There are things called iterated function systems, and there are things called escape time fractals. Those are the main four. There are probably more, but those are the main four I know about. We'll have a very quick look at what those four different types are. So these are random fractals. So things that use a random number sort of generation thing to create things like clouds and random landscapes like that, often used in game creation and that, world creation quite a lot. This approach to create worlds that look realistic. Strange attractors. This is Lorentz attractor, which is an example of a two-body problem, well, three-body problem where you have kind of 2 points of say if this is a body orbiting two other bodies with, so you've got 2 points of gravity, and it sort of orbits around them, but it switches the orbits between the two bodies when they're close enough to each other, and it's really impossible to predict. It's impossible to predict that or describe that because you don't know where it's going to go. It'll always do the same thing, but it's impossible to describe it. And then iterative function systems, which is where you use do something again and again and again and again and again ad infinitum to produce a repeating pattern. And there's some examples of that within the Sierpinski triangle, the Barnsley fern down the bottom, and I think the Hilbert curve and the Menger sponge, which I think is a great name for something. Okay, so those are three of the other ones. The one I'm going to sort of mainly focus on, which is my favourite one because the pictures are nicest, and then the most interesting are called escape time fractals. That one there being the most famous one that everyone knows of, called the Mandelbrot set. So we'll have a kind of look at what that is. So escape time fractals, who are behind them? These are the exciting bunch of people that are the kind of pioneers of them. So we have Lorenz. Actually, in fact, fractals in general, because obviously Lorenz did the Lorenz Attractors, so there he is, Lorenz. There's Mandelbrot, who the set was named after. There's all these other people, Sierpinski from the Snowflake, Gaston Julia, so we'll see a bit more about him. Down the bottom, Udo of Aachen, who Liam brought to my attention earlier on today, who supposedly invented fractals, which is this page there. Which was about how in about 1100 or 1200 or 1200 he used religion to develop fractals, and you can see in this very old painting or etching from years ago, you can see the Mandelbrot set there. That's a complete hoax, so you can read about it on Wikipedia. So he wasn't the person that came up with it. So the person that came up with it actually described not the Mandelbrot set, but something called Julia set, and it was Gaston Julia, I guess, or Julia, I suppose. Don't know, not very good at pronunciation of things. He lost his nose in World War I at the age of 20, and he described mathematically these sets here, that there would be such shapes. One of the problems at the time, obviously, is he was doing that on paper, which he would have spent a long time. He didn't draw that, obviously. He didn't actually draw that. But he was describing these things called Julia sets, which we'll see in a bit. This Julia set has these coordinates, minus 0.75, blah, 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 which we'll have a look at that in a minute. So let's find out more about Gaston Julia. There he is. Unfortunately, he lost his nose, so that's unfortunately how he had to go round for most of his life. And he predicted that some pretty interesting shapes would come out of the iteration of an equation, which was, for a fixed value of c, where z and c are complex numbers, we'll get this amazing sort of potentially interesting patterns out of it. We'll go a bit more into the maths in a minute, so I'm not really going to talk about that anymore. But then this dude came along. So this is, I can't remember, this is sort of like the 20s, 30s, Julia, but then Benoit Mandelbrot came along, and Benoit Mandelbrot is Yiddish for almond bread.
It sounds like that.
Yeah, it does. Right. He was born in Warsaw in 24, and in 1979 he was working for IBM as a computer scientist and got hold of a great big computer. And I can't quite remember, I should remember, but I think he either knew of Julia or was a student of Julia's. So he finally had a computer at his hands that he could actually put these equations and draw these things, because they couldn't really do that before because it was just so laborious. So he came up with the idea of plotting the map of z goes to z squared plus c for every value of c in the complex plane, and a miraculous pattern came out of the trusty old IBM plotter, which was the Mandelbrot set, and hence it has his name. So it's known as Mandelbrot's baby, and I was lucky enough to go to the Arnolfini which is Bristol-based art centre in Bristol back in the 80s, and see Mandelbrot talk about this, and he was going, oh, it's my baby, so he did call it his baby. It had all these sort of characteristics to it. It's got the self-similarity. It's infinitely complex. You could zoom into that till the end of time, and still there would be more to zoom into, and it'd be complex. The area inside, which is the black bit, which is called the set itself, so the Mandelbrot set is the black bit, not the bit outside, is finite, but the border could go on for infinity. The bit outside of it is infinity. You can get loads of beautiful equations. It's easy to program, and it's a pretty simple equation. So just to look at like me and it, and this is a slide that was on my other slideshow, so it's always good to reuse them. So I was kind of into this in the 80s, and I went to see Benoit Mandelbrot, and he signed one of my books. In fact, I got 2 Fractal books signed by him, which I'm really pleased about, which will be on eBay after this talk. And I wrote this program called the Fractal Engine, which I'm going to demonstrate actually, because this is part of my journey of kind of why I sort of ended up where I was. So we got this program, the Fractal Engine, published on a book. So this is an Atari ST emulator. So what we're going to do is switch the resolution, because that's the way Atari STs worked, and have a look at this program. So let's change the preferences. So one of the nice things about this, hey,
I can hear the disk drive.
yeah. So one of the nice things about this is because it's an emulator, I can sort of pimp up my Atari ST and make it a 6860 with a mass coprocessor and a mega RAM, and which I couldn't really do on the old computer. So I'm just going to do that. I'm going to take advantage of the fact I can pimp up my ST, you know. Yeah, a whole mega RAM. I'm going to change the resolution because the ST required you to reboot to change the video resolution. And I'm going to go, Gordon Bennett, right, there you go. It's a bit hard to use. And I'm going to go and widen the screen, and here it is. So Fractal Engine 3, so you can start it. There it is. And you could do all of this with the program, all the exciting stuff.
That's quick. Was that a pre-rendering?
Yeah, it was pre-rendered, it's preloaded. Yeah, we didn't draw it. So for a start, we can draw the Mandelbrot set. If I click that, that was very quick, wasn't it? And then view it. And we can do something like zoom in on it. So let's zoom in on it a bit. Should we go there? Let's have a look at that little baby. And what I'm gonna do is I can increase the number of iterations, which will make the picture look better as we go up. So I'm gonna make this 300, which I wouldn't have done back in the day on the ST, because it would have taken, well, it would have taken about an hour to draw it. So, but now if I draw it, and you can see the self-similarity there, because I went all the way in, and there's another dude that looks very similar to the other one.
What are the gradiated colors outside of the...
That's a really good question. I'll tell you in a sec then. So let's go in a bit more. Let's go in there. And let's draw that a minute. And you can see it's using a method called divide and conquer, which draws a box, and if the whole box is the same colour, it fills it in, which we had to use because it's much quicker to render, otherwise it would take ages on the original ST. So you can see we've zoomed in quite a bit, and you still have the, where's the view? There it is. You still have the self-similar thing. Right, so this is the colours, and we'll come back to the maths of it, but the colours represent the number of iterations it took for the number that we started off with, that we put into the formula, to head towards infinity. And that basically implies that it went to chaos and escaped from the set If it tended to 0, it would have been in the black bit. And what we do is, depending on the number of iterations, we colour it, just to make it more exciting. So what we can then do, armed with that, is if we go to the palettes bit, I think, and swirl. So then we've got, you know, effectively, we've now got about a kind of 1986 Ray video background type thing immediately. So, hey? Okay, so that was basically the piece of software that we wrote back in then, and that kind of was a very complete program, and I'm still you know kind of proud of it. I'm pleased to say I did the buttons, which one of the bits I did with these buttons, which I was very pleased with. Do you like these buttons?
They look like Wizard Amigos page buttons a little bit.
And look, they flash when you click on them. That's quite nice.
Just like our buttons.
Anyway, let's we've had enough of that. We've done that. So let's get out of the.
We needed this cursor.
There we go. So we're out of that's the Atari emulator. And if I can just get the mouse back and go back to the slides.
So the program was literally wrote for Atari.
It was written for an ST, yeah. That's exactly
Atari
it.
computer.
Yeah. Atari ST.
And
Okay, so that was that. And there's the code, and that was Frank. We saw Frank. Right, so then I started, ever since then, I've always sort of like basically tried to write fractal things every time I've seen them. So here's another, this is a rather stupid one. Let's show you that. So this was written in Perl many years ago, and it generates a web page by using it generates a Mandelbrot set using TD tags in HTML with 1 pixel images for being in the set or not in the set, and you end up with that, for example. I won't do a view source on that because it might even still crash my web browser. It was good this, if you put it on a server back 15, 16, 17 years ago and ran it, you could kind of crash things because it just couldn't really deal with the size of it. But yeah, so that was that one. So that was a bit of a stupid approach to doing it. Yeah, I won't do that. It's probably the end of my web browser if I do that. So let's back out of that. And another stupid experiment while we're here was written in COBOL to generate the Mandelbrot set with COBOL. So again, this is probably what Mandelbrot used back in the day, maybe, I don't know. So I was trying to go back. So if I make my screen nice and wide and I've compiled my Mandelbrot set and click that, then I get a Mandelbrot set in ASCII art. So there you go. Anyway, so as you can see, I've done loads of kind of random experiments, and then HTML5 came along, and I thought, well, that's good. I can play learning about the canvas element by just drawing directly in the browser. You know, it's just a little experiment. These days, this is a bit old hat really because it's been around a long time, and lots of things use this now. But it was nice at the time because we now had a bitmap canvas that was in there without having to use things like Java virtual machines to have canvases in web browsers.
Flash.
That was great. And there's the latest version of HTML5 now, which is this month, actually, about 2 days ago. And I also like using the auto design thing in PowerPoint because it does really nice things like why the word great has got a sort of shark. I don't know.
Yeah.
That's good though, isn't it? Anyway, so Canvas works like this. In HTML, you can drop in an element like that called Canvas, and in JavaScript, however you want to do it. This JavaScript's quite old school, probably, but you can basically get a Canvas context and fill in a rectangle in it and colour a point. So armed with that, I'm going to have a look at how to do that. So here's the main bit of the hard math stuff then. So let's just go back and just work out what we're actually dealing with here. So we're talking about imaginary numbers. Who here in the room knows about imaginary numbers. Yeah, we got fairly. So let's have a quick look at them and recap. Okay, so first of all, square root. We all know what a square root is. It's the inverse operation to a square of numbers. So if you've got 2 times 2 equals 4, therefore the square root of 4 is 2. And again, 9 nines are 81. Square root of 81 is 9. 25. A number that, you know, computer people obviously memorise off by heart, that 256 squared is 65,536. And for some reason, this, obviously I just showed you that this, obviously the square root of 65,535 is actually not a number with loads of numbers off the decimal point. Don't really mean anything, that. But there you go. So, imaginary numbers, what the hell are they? So those things are called real numbers. Imaginary numbers. So the problem is we've got this operator called the square root, but we have a number line that goes in the positive numbers and negative numbers. So we've got a problem is we can actually apply the mathematical operator to -1. Sorry, the square root operator to -1. But what the hell is that? Because obviously -1 times -1 is 1. So what is the square root of -1? And the answer to that is, well, we don't really know, so we call it I. Which is called the imaginary unit or imaginary number. So, therefore, if you square I again, if the square root of -1 is I, and you multiply I by itself, you get 1 again. You get -1 back. So it works exactly the same way as the other side, apart from with i's. So if you have 2i times 2i, you get -4. Right? Because that's splits out of the fact that if you multiply those two numbers, 2 times 2 is 4, times I is -4, because I times I is -1. That makes sense? So you can kind of, the maths works that way. Thanks to Naomi for that extra tip there. So 256i times 256i is -65,536. So this guy originally thought of it. Hero of Alexandria, didn't call them imaginary numbers, but had thought about working in that area of square roots of negative numbers. So quite a long time ago. I don't know that much happened. I think he did it then, obviously Alexandria collapsed and the Roman Empire collapsed, and then people were just sort of banging rocks together for quite a long time.
He did it to win a math contest.
Hey?
He did it to win a
He did it to win a math contest, did he?
Yeah.
Wow.
Yeah. So he could solve things more quickly.
And did he win the maths contest?
Oh, yeah.
Should have done, shouldn't he?
He is the hero.
That's where his name comes from.
Then there's another chap called Raphael Bombelli, who I couldn't find a picture of, but he then first started then picking up on this maths and using it in the 1500s. And our old friend René Descartes was a bit cynical about this maths and said, oh, this is a load of rubbish, and called them imaginary numbers. As a put down, and it's actually what stuck to the name and the numbers. So it was René Descartes, who though didn't really believe in them, thought they were a bit silly, actually named them. And then these two, Euler and Gauss, who then actually sort of then took the maths and did some proper stuff with it. These two, Euler and Gauss, are very important people in math circles, really. Anyway, so those are the dudes, and yeah, those are called real numbers. We said that, didn't we? Any questions at this point? All clear? Yeah, great. So now we're going to look at something called complex numbers. So we've got our imaginary numbers, but there's now something called a complex number. So that is, you take our real numbers, the ones without i's, and you extend them by adding an imaginary unit to it. So you combine a real number and an imaginary number together. So they're normally expressed in the form of a plus ib or x plus iy. And so the a is what they call the real part, the ib is the imaginary part. I is I, and a and b are both real numbers. And we'll see more about that in a minute. And the set of all these complex numbers in maths is denoted by a capital C like that. And you can plot these numbers on a graph with a pair of coordinates, like almost like Cartesian coordinates, which is ironic because obviously Descartes was cynical about all of this, in the sense that you can use the x-axis as the real plane down here, and then the y-axis is the imaginary plane going up. So you have a vector that represents this number. So what we're going to then do is plot what's called an iterative equation on that complex plane, right? An iterative equation is effectively where you put a number in, you get a number out, and then you put that number back in, and you keep doing that for a certain amount of time. So the output goes back in to the input. Okay, so what we're going to do to draw the Mandelbrot set here, and you can see that we've got it put on a piece of graph where you can see the real numbers going from positive and minus, and the real components of the complex numbers going from -2 to 2, and then the real and then the positive and negative imaginary component on the y-axis going from about -1.25 to plus that. So we're going to go through all those numbers that appear on that. We're going to set Z, the starting point, so the number we always start with Z is 0, and then for every value of C. Does that make sense?
Yeah, so there's a capital C is the set, and then that lowercase c is representing each value within.
No, the C. No, sorry. Z and C are just values. The capital C isn't the set.
Well, in the previous slide, I thought.
It was, but it was in an italic. It's in a. The C is
so
represented
it's
by an italic,
totally different.
by a serifed letter. Yeah, it's a bit confusing, really. Maybe I should. It's normally written Z squared plus C like that. So yeah, it's a good point.
But the C for every value of C, that one is the set, right? At the top, the second sentence.
So C and Z in this are not the set. They're just complex numbers called Z and C. That's it.
I think like that, the one that says for every value of C in the place could be written for every value of C in C.
Yeah.
Yeah, it could be written like that. That's true.
Yeah.
Thanks. And for every so what we do is we set Z to 0, and then we plumb Z and C into the iteration.
Too late, mate.
There might be more questions.
Okay. Okay, so we're going to go around. So we're going to start with Z is 0. We're going to put it in, compute it for a certain value of C. So we're going to start off with, say, the initial value might be C is -2 plus -1.25i. That will be the starting point in that, and we'll move all the way to the other side of it. And we're going to start with Z is 0 and put it into that equation, and we're going to see what happens to Z, and then at the end of that, we'll do the next value of C. Right. So if Z tends to, i.e. Z sort of heading towards it being 0, then we say that C is within the set. And this is the order. So that's the black bit there. All right. And if Z is then the value that this iteration is doing is tending towards infinity, then we say that C is not in the set, and this is chaos. So chaos is outside the set. Okay? Right, so let's look at the maths of how we do that and turn it into an algorithm. So basically, so we're gonna write Z as I said, as they're complex numbers. So x plus iy is Z, and a plus ib is C. So how do we multiply them together? So if we write them out like that, because the equation is Z squared plus C, and then if anybody can remember multiplying things in quadratic equations, you would multiply the left of the first part with the left and right of the second, and then the right of the first part with the left and right of the second. So you end up with x times x, y times y, and then x times y twice, so you get 2xy. And then we've still got to add a and b to it at the end. All right. So you can compute that out and tidy it up a bit, so that then x plus iy. So for each complex number you put in for z, so 0, 0 to start off with. So if you put 0, 0 in, then that becomes those numbers go through that equation. Okay, does that make sense, roughly? Yeah? Cool. So a little bit more just to finish off. Computer normally cannot handle complex numbers directly. So we split up the real and imaginary parts to form two equations and calculate them separately, because most computer, C++ does have a complex number type. There's probably some other programming languages that do, but most of them can't. So that was from the previous slide. I've just written it out slightly differently, but effectively x squared minus y squared plus 2iy plus a plus ib. So therefore, our x component has all of the real stuff, because if you remember, the real numbers are on the x-axis, and the y is the imaginary. Okay, so hopefully that makes sense how those bits got pulled out. Okay, right, great. Any questions at this point? Are you right? Yeah.
So I suppose then, how integral then is the capability of the computers to the perception of the fractal?
I guess the better, well, really, there are a number of things. Obviously, the maths, the more accurate the maths, then slightly better.
Sure.
But especially if you zoom in more.
Yeah.
I mean, from the initial rendering,
Sure. Yeah, that's plottable by human comprehension.
And then secondly, obviously, it's the processing power of the computer.
Okay.
So there's two things that happen. So one thing that would happen is, on something like an Atari ST, it's a 16-bit computer. I can't remember what the how small a number it's able to store. But you'll come to a point where it all breaks down because the computer can't store smaller and smaller numbers. So if you zoomed in on an ST, you just get to a point where it sort of just stopped working properly.
Sure.
And you've got wrongness. So you've got that element. And then obviously also it's how quick you can draw it. So the processor power of it is really important, because if you want to zoom in and it's going to take a week to get the next picture, it's very slow as opposed to.
So, but when you say that you've split the numbers into real and complex, and then have assigned them various positions on the graph, then that is not altering then the representation of the fractal.
No, not really, no.
Okay,
Yeah, so there's two things. We'll see in a sec. There's the maths bit of it, the computation of it, and then there's the rendering part of it. And there's different options on the rendering of it. Like, for example, one of those earlier screens, we had a sort of 3D view. So you could, there's obviously, I don't know if that answers your question, but...
No, enough.
Okay, so we can transfer that into an algorithm. That's not in a particular language, really. It's just in a sort of general computer algorithm for a Mandelbrot set. And so our broken down maths is in between the while and the end while loop. So this would, if you can see, for a given value of C, for C coming in the top, so it says mset level at the top, it takes three parameters, the real and imaginary components of C, and then the maximum number of iterations that we want to actually do, which we'll explain a little bit more in a sec. We set x and y and x squared and y squared. They're just represented by x2 and y2. It's quite common in writing maths computer programs to do that. They're all set to 0 at the beginning, as I said, and then we are going to have two conditions in the while loop. And the two conditions are given our maximum number of iterations. So that is like, how long are we bothering going to keep putting z in the equation before we get fed up and say, well, we've done this enough times and it hasn't gone to infinity. That's the first bit. And the second bit is saying, actually, if the squares of those two numbers, the sum of the squares of those two numbers gets to be a much bigger number, in this case we've got 10,000 here, then we are going to consider that going towards infinity. Okay, so there's two sort of break conditions in this thing. If we broke with the first condition and we basically, the number of iterations hit the maximum number of iterations, then we're going to say, that's in the set, right? And z was going towards 0 because we did it 100 times and it never got chaotic, so we reckon it's going to be ordered. If it breaks out on the other one, then we're going to say, right, well, it wasn't in the set because it headed to infinity quite quickly. It got to that big number, and we're going to use the number of iterations it took to do that to maybe do something interesting with how we plot it. So we'll look at that bit next. That's the same thing rendered in JavaScript. Doesn't really, you know, make too much of a thing. The 10,000 is represented by threshold there, which can be put into the function. So that will compute 1 point on the thing, on the graph. So how do we plot the image then? So what we do is we've said that if Z tends to 0, then we say that C, because that's the actual thing we're doing, is within the set. And therefore it tends towards order, and we will colour it black. Right? You could colour it a different colour, but we're going to call it black. It's normally black. If Z tends towards infinity, then we say that C is not in the set and tends towards chaos. And then we colour it non-black. Okay, in that previous picture, it was just white. In Mandelbrot's day on his IBM printer, it was just white. So it's a black and white. So the black pixels are in the set. That's the Mandelbrot set. The orderly part that is not tending towards infinity. That's the part on the inside. The colourful part is the chaotic part that tends towards infinity. So what we then do is say, given you, on the left-hand side, what they've done is, on that picture, is said, depending on the number of iterations it took to escape, to go to infinity, colour it a different colour.
Well, to go to the threshold.
To hit the threshold, yeah. Yeah. So if it did it quickly, it gets a colour, it gets a certain colour. So the further out you are from the set, normally, is the quicker it went to infinity, basically. So the quicker it went to thresholds. You put the number in, and after 2 iterations, it was already at 10,000. So when you zoom in on fractals and look at them, the most interesting places to look are not obviously in that big sea of blue, because it will just be a big sea of blue if you zoom in there. And the bit in the set isn't interesting because it's just black, but it's the boundary between chaos and order, which is probably like life, really. That's the interesting thing, is that boundary there. So the plotting code for doing this is, so remember the Mandelbrot set that we've got here, we start with Z is set to 0, and we take every single value of C and we plot it on here. So if you look at this algorithm, it would really help if I put line numbers on, but you can probably see that I sort of bolded a couple of things, and in the bolding of it, we have C here is set to a different value every time in the for loop. So that's how we're doing every value. And you'll see there's a bit where it says const point x is 0, y is 0. So that sets it to 0. And you can see that based on that while loop that we had previously, what we're saying is if we hit the maximum number of iterations, so say we went around 100 times and it didn't go past the threshold, then we'll colour it black. If not, we're going to set it to a number from our colour palette that we compute based on the number of iterations. There. So, right, so the next bit is, that's the Mandelbrot set, and we're going to see a demo of this shortly, and then it will all be over. So, having done that, what the Mandelbrot set is every value of C, and each time you start with Z equals 0. The Mandelbrot set is considered the set of all Julia sets. Because remember Julia, the guy without the nose, he defined Julia sets in actual fact. So this is basically the set of sets. So each point on there, each value of C has its own associated Julia set. So we can do a similar equation that's very similar, but what we do is we fix the value of C rather than calculating it for everyone, and then we take those fixed values of C and do the equation for every value of Z. So it's a slight sort of change on it, and that gets us these different patterns, and we'll see the relationship in a minute. But the code difference, again, I've tried to bold it to highlight it, but you can see that at the top, C now, instead of being set each in the for loop, they're now set above as two constants and they don't change. And then you see that the where it says Z, each value of Z is now the thing that's calculated in the loop, the starting point, rather than setting it to 0 every time. So let's just have a look at it. So here's one I prepared earlier. Right. So this is the kind of that put into effect. It is very simple. I've always meant to do add more features to it, but so basically I'm gonna turn that off for a sec and just show you how it works. It might be good to zoom in a bit. There. All right, so I can change the number of iterations there. I think it's set to 110 at the moment on the Mandelbrot set, and I can go to each one. And you remember I said a point on the Mandelbrot set is all of the Julia set. So if I click on the point, on the right it draws the equivalent Julia set at that point for me. Right, so there's an auto draw thing, so I don't have to, so if I come in, you can now see that for values, hang on a minute, oh yeah, there's a delay, isn't there? I'm moving my mouse here. So towards the outside of the set, there's basically almost nothing there, and I've gone too far. Hang on, this is quite hard. There's almost nothing there because we're way out of the set. We're way out of it, and there's only a few little bits for these points here. These are called Cantor Dust, these things, after that other guy, Cantor. As you come in, you start to get more of a set that makes some kind of sense, and if maybe we come in this sort of little tendril here, you can see that it starts to come together like that. And then you can kind of navigate. And you come into the set, now we're inside, you can see that it's got a pattern. If we kind of go to the end, it starts to sort of drag out that way. And we can come back in and down. And, you know, you can there's endless, infinite.
Yeah, just movement across the axes is quite interesting.
Shapes, look at that one. That's a bit like the one that was on that slide earlier on there. Right, and as we head towards 0,
Where is the y-axis?
Zero's here somewhere. You can tell where 0, 0 is because it becomes, somewhere around here, it becomes sort of a circle.
Yeah.
And as we go to the Mandelbrot set's anus, here, it produces a different shape like that.
Lovely.
And
so, but that's in the positive integers of the real numbers then.
so now x is a positive number, and y is a positive number up here.
Yeah. Okay.
And you can see it reflects across the axis. So actually, across the imaginary axis, the values are the same. So it's identical. It mirrors.
Sure.
All right. So that's that. You asked about different ways of drawing it. There's a method here called the binary decomposition method, which kind of does a kind of sort of weirdy sort of checkerboard version of it.
Oh, great.
Does that have any zoom on it, on that one? Because the zoom is a cool thing, isn't it?
So if you press Z on the keyboard, it says zoom mode coming soon.
Yeah. When?
I don't know. When I can speak to Joshua about how I can kind of get some funding, how I can set up some kind of funding.
Very soon.
Okay, so that's it. Yes, Zoom will. I'm kind of inspired to work on this and actually finish it and re-implement the rest of the Fractal Engine. For the
Can you just
SD
move around with the mouse a
on
bit more?
here.
Because it's really pretty. I like it. Yeah, just.
We can go back to the other thing and do the zoomy thing.
This
Is this
really
online?
Nice.
Yes, this is online,
One question.
so you can play with this.
don't have to take it.
But I cannot take it. I give it back.
Yeah, I've really kind of finished, so I can do questions.
All right.
Thank you.
So, did I understand that, like, when you go to one point in the Mandelbrot fractal, that it uses that for the formula for the Julia set? Because
It
that's what I
does.
was
Yes.
wanting to say before. Like, oh, it's interesting, but it always takes like the same number and feeds it into the same equation. But what if the equation would change? But like, kind of that's what it's doing already. But not in random
Yes.
ways, but somehow based on an original.
The equation's the same, but the starting points of x, z, and c change.
Could you do it the other way around too? To make like a Julia set and then go around and use that as an input to define the Mandelbrot? Maybe that makes no
I
sense.
suppose it doesn't really make any sense.
Does not? Okay.
Not really.
You got a different C.
I don't think it makes any sense.
It doesn't
It
make
would
sense.
be sort of like you can like look at a map. So the Mandelbrot set's more like a map.
All
You
right.
see what I mean? And you can look at the map and you can say, right, I'm going to go to there. I'm going to go to Daniolan. And you can go to Daniolan, but when you're in Daniolan, there's nothing you can really do to get back to the map, if you see what I mean, apart from getting the map out again.
Does the like what I imagine is the Mandelbrot zooms, but the Julia one doesn't because it's like a snapshot, or is it maybe
so
that's
you
wrong?
can zoom into the Julia set.
Yeah.
You can do Julia zooms. They're not as interesting because the Mandelbrot set contains all the Julia sets, so it varies much more.
Yeah, that's
Whereas the Julia set is much more self-similar. So if you keep zooming in on it, it looks quite samey. But you can still get some really nice pictures, especially those the ones that are around here. Ooh, like up there, quite nice these. And we can change the iterations as well, which will make it a bit slower, but will give us maybe more. I mean, at this screen definition, it's not. You don't really get a good there you go. You sort of get a bit more detail with higher number of iterations and stuff.
And the other bit is in like the chaos area on the Mandelbrot set. In the previous one, the number of iterations decided the color. But in this drawing, it's like either black or white in a sort of nice
is.
pattern. Which,
Yeah.
like, how do you go from number of iterations to black or white in an interesting pattern?
This still uses a sort of similar thing, which is kind of level sets. So like you've got each iteration level, you've got a band around. So they're the same. So the bands are in the same places as the colours are, but it uses a way of working out whether it's black or white, alternating,
You could
based on
switch.
the angle, I think.
Could you switch between them?
Yeah, if I switch back to the other one.
Yeah, there's no detail at all where there's an interesting bit. Like, I was looking somewhere on the left in the top quarter of it.
Oh, what, here?
No, in the chaos bit, quite far, around there. And on the black and white one, there was a sort of, area where there's black and white and black all joining in a 4.
Oh, yeah, that's
thing.
quite nice, isn't it?
Yeah, and there's no sense of that on the other one.
No,
Yeah.
I do quite like the binary decomposition.
Yeah, it's
approach.
funky.
It's quite interesting. You can do all sorts of things with this more than this. You can obviously use colours for that as well. So you could actually combine the two and have different colours. You get binary 2 colours, or you could have multiple different colours. You can do internal colouring as well. So you can actually do some kind of colouring still based on. Although on the inside, I can't remember the approaches for internal colouring.
Yeah, because the black and white, I would have thought it's less information because it's just black or white, but there's actually more detail in the chaos bit, like in the far out sections of the chaos bit, than in the colour one, which,
Yeah, that's true. So anyway, that is actually online. I'm running that locally at the moment, but there is a web page. You can get it on. You can get it on GitHub and download it and improve it and laugh at my JavaScript, which is very old school, and everything like that. And maybe one day I'll improve it and have a Zoom, which I quite like to add the zoom really. And maybe draw some other fractals, because the other thing is the one thing the Atari version did. You don't have to use z goes to z squared plus c. You can actually use different mathematical formulas as well. This is just one of them. So you can do some really interesting shapes by applying using formulas with cosines and sines in them and all sorts of mathematical operators. So you can get some really other different pictures out of it by playing about with equations and maths and that sort of thing. So just to kind of go back, so there's a link to it on the slide, and where are we? So you can go and do that. That's a nice zoom on YouTube, which we could look at later if you want. So in summary, fractals are pretty and still cool. So I don't know if anyone ever remembers XHTML 1.0 and 1.1. It was all really nice and clean, but so much so that people forgot to live a little. The web got really kind of austere and specified and dull. So HTML5, when it came along, it made it kind of sexy again, basically. Reconstructive surgery has improved greatly since Gaston Julia's time. Poor chap. And maths is hard, but it can be fun. And that's it. Thanks very much.
Woo!
And that one on the right, actually, what I said is a cosine, is a Mandelbrot set of a cosine.
Wow.
The tie-dye T-shirt, I think.
Yes, definitely.
Mike, can I ask you, do you have in mind any practical applications of fractals?
No, my mind doesn't really work like that.
That's fine.
So I just think they're like cool pictures.
Great, me
and
too.
They were great for making, putting on covers of albums in the late 80s, early
So
90s.
they might have their time again.
Yeah. So.
Yeah, sure.
Yes,
yeah,
of course. Generating landscapes is quite good.
Yeah.
Generating computer landscapes
Sure.
and stuff. But yeah, I can't think of, we were talking earlier on about NFTs or something.
Mm-hmm. Is that practical?
I've got no idea. I don't know.
I mean, NFTs in general are anyway just like a proof of authenticity. So if you would want to create art, and then, like, for example, you could make some story out of it and say, like, okay, I generate some kind of series, and then I publish it as NFT, and I'm the owner of this. That means that from every sale of NFT in the future, you get some kind of little fraction, and this you donate for research, math research or something like that. Like you can come up with some kind of a scheme,
You
but
could do, yeah.
or to include this in a art project, but not needed, of course. But it's a way to monetize something and then do something with that money.
That's true, yeah.
I have just one. The set of C of imaginary numbers. I was just trying to imagine what they were. Like, can you say like the first 3 or 4? Are they things you know what they are? Like the set of them all.
Well,
is it like square root of -1, 2 square root of -1, 3?
well, no, because okay, if they're whole numbers as opposed to rational numbers, they would be I, 2I, 3I, 4I. But obviously, if you bring, because you can have obviously, numbers with decimal points in and stuff.
So is it the set of whole rational numbers multiplied by I?
Yeah. Well, any number. So it could be 0.00006I. So on that plane, we're looking at points from, I think it's like about -2.
That's because on one of them you had Y resolution, which was the resolution of the rational number
exactly. If we were
multiplied
to
by
go
I. Yeah.
back just a little bit,
That one's got Y
that one's the better
resolution.
one.
Oh yeah.
It's the Mandelbrot set.
Or it's X resolution. Oh, X resolution and Y resolution. Yeah.
So the X resolution, Y resolution is obviously like on that thing you saw. It's 640 by 480 or something. Is the picture, and yeah, it just takes each of those values. But it doesn't take 640 by 40. That's a screen resolution. It's the complex plane, so it would be like -2 to another number that's bigger than that. So yeah, that would be it. So for example, just to show you very quickly, if we use the where are we? Right, yeah, if we use the COBOL version of the code, yeah, you can see here, so the resolution of the drawing that we're doing is 240 by 100, and then the plane, the real plane min and max is -2.5, and the maximum value is 0.8, and then the imaginary plane is from -1.25 to 1.25. And so therefore what we're doing is we're going to basically work out the proportion of those numbers, like what does each pixel represent, and then we go around each pixel, we'll compute it back. Does that make sense, really?
Enough sense.
Understanding, we can do a separate workshop on COBOL if you want, obviously. That's it. Yeah.
Yeah, thank you.
That's right.